So why do we care about particular solution problems? Well, we care about them because they have amazing applications. So it says in the previous section, we use the general position function of, and this is neglecting air resistance. This would be like if we dropped a ball straight off of a building and there were no air resistance. We determined that it was negative 16t squared plus v naught t, where v naught is your initial velocity, plus s0, where s0 is or s naught, which is the initial height. So for instance, if I just dropped a ball directly off a 100-foot building, it would be negative 16t squared. My initial velocity, because I just dropped it, I didn't throw it down or up, would be 0, so that middle term would cancel, and then I'd have plus 100. That would be my position function if I dropped a ball from a 100-foot building with just dropping it, not pushing it, throwing it up or down when I dropped it. So that was our initial position functions. And this was that negative 16t was because we were measuring gravity in feet per second. Actually, acceleration is feet per second squared, but that's what that negative 16 came from, gravity. And this is really cool because we can figure out exactly how we do this and why this is. All right, so it says, let's look at example 8, deriving a position function. Derive the position function when a ball is thrown upward with an initial velocity of 32 feet per second from an initial height of 48 feet. When does the ball hit the ground? With what velocity does the ball hit the ground? So we could use this original function, plug in the given information, and see what we should get. So let's figure out what this is. So it says the initial velocity was 32 feet per second. Upward, so that means the velocity is positive, an initial height of 48 feet. So what we should have is s of t equals, well, we should have negative 16t squared plus our initial velocity, it is positive because we threw it upwards, would be 32 feet per second, so I should get a 32t, and then plus we should have our initial position, which is plus 48 feet. So this should be our answer to the problem, negative 16t squared plus 32t plus 48. That should be our answer to the problem, but I want to derive it from the ground up because that's what it tells us to do. Okay, so how are we going to do it? Well, the first thing we need to know is what is acceleration. On Earth, acceleration is due to gravity, and gravity is measured at a rate of negative 32 feet per second, or feet per second squared. That is the acceleration due to gravity. So that is a of t. I also want to remind you of a little bit of something here. You have your initial position function, and then you have the derivative of the initial position function is the velocity function, and you have the second derivative of the position function, which is the derivative of the velocity function, is your acceleration function. So what I'm telling you right now is that your acceleration function is negative 32 every single time due to gravity on Earth, again, assuming no air resistance. So if I know the acceleration function and I want to integrate the acceleration function, if I integrate the acceleration function, I'm going to get the velocity function. So let's give that a try. Let's find acceleration. Again, to find the acceleration function, let's find velocity. To find the velocity function, I need to integrate the acceleration function. So velocity is the integral of acceleration, which in this case is the integral of negative 32 dt. Well, the integral of a constant is that constant times the variable, in this case t, and then we have the plus c, right? So this is our velocity function, but this would be the general solution for the velocity function. Well, we know what our initial velocity is. Our initial velocity is 32 feet per second. So we know that our initial velocity, in other words, v of 0 equals 32. So what does that tell me I need to do? Try plugging in 0. That would be negative 32 times 0 plus c, and I must get 32. That tells me that c equals 32. So that's my initial condition problem. So I know my exact velocity function problem. My exact velocity needs to be negative 32t plus that constant, which was plus 32. So there's my velocity function. Once I know velocity, I can find my position function. How do I find my position function? Well, to find the position function, you need to integrate the velocity function. Okay, so to find the position function, what we're going to be integrating is the velocity function we just found, which was negative 32t plus 32, and that's with respect to t. Well, what's the integral of negative 32t? Well, that would be the negative 32 times t to the first power, so we have to raise the power by 1 and then divide it by the exact same thing, plus the integral of 32 is 32t, the integral of a constant is the constant times the variable, plus the constant. So our position function is negative 32t squared over 2 plus 32t plus c, but of course we could simplify that. Look what we're getting. We're getting the negative 16t squared, because the 32 and the 2 simplified, plus 32t plus c. We need our last initial condition. We know that the initial position, or the initial height, was 48 position, so we know that s of 0 has to equal 48. Let's see what happens when we plug in 0 into our into our position function. That would be negative 16 times 0 squared plus 32 times 0 plus c, and that has to equal 48. So that would tell me, because we have all the zeros, that tells me that c equals 48 in this case. So now I'm going to plug that c value back into the position function to get the true position function, which would be s of t equals, well, we would have negative 16t squared plus 32t plus our c value, which was 48. If we go back and look according to the formula, looks like those are the exact same functions to me, negative 16t squared plus 32t plus 48. So we were able to derive why that had to be the initial position function. So now let's go back and reread the problem and make sure we're actually solving the problem. It says, first question, when does the ball hit the ground? So when does the ball hit the ground? Well, that means that my height, or my position, has to equal 0. So what I'm looking at is, when is s of t equal to 0? Let's go ahead and solve that now that we know s of t. That would be negative 16t squared plus 32t plus 48. We set that equal to 0. We need to solve this quadratic equation. You could use the quadratic formula. What I'm going to do is, I notice they picked really nice numbers here. I'm going to divide everything by negative 16 because it is divisible. Every number is divisible by negative 16. When I do that, I'd end up with t squared minus 2t. 48 divided by negative 16 would be minus 3. That equals 0. So I need two numbers that multiply to be negative 3 and add to be negative 2. That would be a negative 3 and a positive 1. I set each of those factors equal to 0. T minus 3 equals 0 would give me t equals 3. And t plus 1 equals to 0 would give me t equals negative 1. That's before the ball was launched, or whatever it is. It is a ball. So that's before the ball was thrown. So the only thing we need to worry about is t equals 3. So it hits the ground after 3 seconds, or at 3 seconds. 3 seconds after it's been thrown. Okay. Let's look at the next question. What did the next question ask? It says, with what velocity does it hit the ground? Well, we have our velocity function, and we know when it hits the ground. It hits the ground after 3 seconds. So now we just need to find the velocity at 3 seconds. So that would be negative 32 times 3 plus 32. Negative 32 times 3, which would be a negative 64. So what velocity is it hitting the ground at? It's hitting the ground at negative 64 feet per second is the velocity that it hits the ground with. Again, velocity is measured in feet per second. The original problem should be feet, and then the acceleration would be feet per second squared. That negative sign here, all that means is it's decreasing or approaching the ground at a velocity of 64 feet per second. We do need the negative here just to indicate direction. It is going down. If we put positive 64, that means the ball would be going up. So be careful with your negative sign there. Okay, so let's look at the last problem on this page. Hopefully not too bad for us. It says the marginal cost. If you remember, the marginal cost is c prime of x, is the derivative of x. Production is modeled by d of c over dx equals 28 minus 0.02x. It says it costs $40 to produce 1 unit. That's an initial condition for us. It says find the cost of producing 200 units. So what we know is the derivative, c prime of x, is equal to 28 minus 0.02x. Okay? So if we want to find the original cost function, what are we going to do? Well, we're going to integrate the derivative. So that's the integral of negative 28 minus 0.02x with respect to x. The integral of 28 is 28x. The integral of negative 0.02x would be negative 0.02, but then it would be x squared divided by 2. Don't forget we have the plus c. I'm going to clean this up for us. I'm going to say my original cost function, that 0.02 and that 0.2, and I'm going to write it in descending order. So I'm going to have negative 0.01 x squared plus 28x plus c. That's my general cost function, my general solution. But I need to find the particular solution. I use the given information. So what do we know? We know that the cost of 1 unit, if I plug in 1 unit, I have to get $40. So let's figure this out. If I plug in 1 unit to the cost function I just figured out, I'd have negative 0.01 times 1 squared plus 28 times 1 plus c, and that has to equal the cost of 1 unit, which was $40. Plug this into your calculator, solve for c. Looks like I'm getting c equals $12.01. So that's going to be my c value. So my actual cost function would be negative 0.01 x squared plus 28x plus 12.01. That's my real cost function, but let's go back and reread the problem. The problem didn't want the cost function, it wanted the cost of producing 200 units. So what do? Simply plug in 200. I have negative 0.01 times 200 squared plus 28 times 200 plus 12.01. Plug that into your calculator. Let's see what you get. I'm getting the cost of producing 200 units would be $5,212.01. So again, we integrated, we had our arbitrary constant, we used our initial condition to find the true cost function, and then from the true cost function, we were able to figure out the cost of producing 200 units.